Okay, my friends, I'm hoping to have a very good time here today. I have the electron dipole flood theory, which says that protons are not made out of one big positive thing with a few quarks and a couple of this and that in there. They're made out of 1,823 literally bar magnets, little bar magnet type dipoles. And that was what makes up a proton. 1,824 is an even number, so it's uncharged, so it becomes a neutron. Light does not flap like this. Light spins like this, and the smallest particles attached, two of them together, actually this is one, but two of these together would be light flowing through the air. All right, so we don't understand light, we don't understand atoms. There is no such thing as the elements. You see that? You say, oh, that's hydrogen. Well, what is hydrogen made out of? Well, it's one big positive core and one little electron. No, it's not. It's 1,823 or so dipoles, and then one more wants to get in and says, no, you can't get in, we have enough. 1823 is all we want. I'm going to push you away to a certain distance. And that's where the electron sits. But it sits outside of a whole batch of electrons. The same number of what we would always call proton, here's where it gets a little tricky. A dipole is a positive and a negative. It's a bar magnet. You know what a bar magnet looks like? It's a positive and a negative. Well, in the case of down in light and in the atoms, we could separate those. You cannot do that with a bar magnet. You can break it in half and you get two bar magnets. You break it again, you got four bar magnets. You keep going. But once you get down to here, into the nucleus, you actually can break the black away from the white. The bar magnet parts can separate. I never thought it was possible, but I can do it, and I can show you. It's not hard to do at all. All right, I said it's not hard to do at all. Separate the positive from the negative. It's not hard. This is what light looks like when it's in its photon phase. That's a bar magnet. That's a bar magnet. The two of them stuck together make a photon. Half of them, just one of those, the black and white, is what we would always have called an electron. We never knew the black was there. That's why it's called dark matter. Nobody's ever seen it before. The only reason we can see it is because we accelerated the light, the black and the white together, and then exploded it right here at the Venturi, and the black sits on top of the white. All right, nobody's ever seen this before because they didn't use CMOS, which is complementary metal oxide silicates, which give off these luminosities when they're excited. All right, so before they were going inside and taking away some of the energy, and they messed everything up. It was called the observer effect. We don't have that because all we're doing is looking at the light that hits us. We're not interfering whatsoever. Before they had what they call charge coupled devices, and they put them inside and they'd get charged up, and then they'd see what the charge is. Oh, that means it's doing this and that. No, you just sucked off a bunch of the charge. You have no idea what it did. And here is light accelerating. All right, very simple. To a Venturi, which caused it to start to glow enormously. That is an increase in energy from here to here, and we did nothing whatsoever other than put just a block of a Venturi here. So they had to force all these fields to crush to get through there, and the only thing that squirted out was the white. The black didn't come out at all. You see that? All that came out was the white. The black particles got pushed back because they can't fit through. They came back and reattached out here. This is fission, that's fusion. Sabine is correct. We need new physics. She's been talking about this now for a year, and I've been trying to get through to her to discuss it with her because she has a voice. She's got a bazillion hits. I don't get anything. But I'm showing the particles. She's asking the questions. I'm showing the answers. Sabine, talk to me. All right, I haven't watched this at all. I haven't seen any bit of this. All I got to hear is to see, I constantly hear physics claim there is something wrong with what? With physics. It just doesn't work. Nothing they say is correct. I'm serious, nothing.
I constantly hear physicists claim that there is something wrong with our understanding of the universe. It's an argument they frequently use to justify new experiments, a better detector, a new telescope, a bigger collider. At the same time, they'll also tell you that try as they might, they can't find any evidence that disagrees with their best existing theories.
I got all the evidence, everything I can show you totally destroys the fact that there's even elements. There is no elements here. You see helium? Helium's supposed to be 2 protons, 2 neutrons, and a couple of little electrons. Well, guess what? It's 7,352 particles. And the only way you can make life work is to be able to divide these things into every single different little piece of them. And whenever you see, you probably, I don't know how familiar you are with chemistry, but if you don't know what an isotope is, you have no idea what chemistry even is all about. Let me show you isotopes, and I'll show you there is no such thing as any of these particles. They don't exist. There's only zones of stability. But between the zone of stability and the next zone of stability, there's thousands and thousands of different literally molecules that exist in there. And they have to exist because when life sends in the chemistry to create the products you need for your life, it does it like that. Hundreds of thousands of breakdowns of these particles happen in 1 second from one enzyme. Enzymes are the thing that makes life work. Life couldn't possibly exist with this number of elements. It's impossible. They break down so many variations of these particles in an instant. 1 second, hundreds of thousands. Okay, this is going to get a little complex, but if you're interested in reality, stay tuned. How many reactions do enzymes carry out each second? First of all, what's an enzyme? An enzyme is an extremely elegant molecule created by a bacteria. And you have thousands and thousands and thousands of different bacteria in your body, different species. Each one of them creates an enzyme, and that enzyme does this. Wait till you hear what an enzyme can do. We normally think of all of these molecules, elements, as pretty stable. They are not stable at all. There is zones of stability, and then in between there's thousands of different zones. Listen to this. The biochemical reactions taking place in cells, though thermodynamically favorable, are in most cases very slow if left uncatalyzed. That means if there's no enzyme, nothing happens. An enzyme is a catalyst. So if there's no catalyst, nothing happens. It's very slow. For example, the spontaneous cleavage of a peptide bond would take 400 years. 400 years at room temperature. It takes done in the body because of an enzyme. It would take 400 years, and phosphomonoesters hydrolysis, routinely breaking up TPP to release energy, would take about 1,000,000 years. 1,000,000 years in the absence of the enzymes that shuttle that reaction along. It goes, they're breaking down thousands of different little particles instantaneously to come up with a product which is biological. 400 years to break a peptide bond, 1,000,000 years to break apart ATP. That's your energy source. This is so not understood, it's just beyond my belief. And it all boils down to electron flood theory. Because there is nothing but dipole electrons. There is no big, huge protons. A proton is made of 1,823 dipole electrons. And for every proton, it's 1,823. For every neutron, it's 1,824. So as you go up into these huge numbers of protons and neutrons, multiply every one of them times 1,823 or 24, and that's the number of particles that exist in aluminum or silicon or phosphorus, or, all these different, what we call elements, are huge, huge, huge masses of little dipole electrons. And in between all those masses, there's a ton of what they call isotopes, which are semi-stable. And then there's a billion other literally probably billions of other particles that are not stable, and they just happen instantly like this. 1,000,000 years it would take without an enzyme. So with an enzyme, done. I'm just going to give you one example, but they all have the same thing. They have isotopes. And what is an isotope? This is carbon. We're supposed to be carbon-based creatures. Well, we got all kinds of carbon. Not just one carbon. They call them all having 6 protons. Z means the number of protons. Okay, it's atomic number. Then N is the number of neutrons. Look at this, 6 all the way down. Then they say, well, then this one's got 2 neutrons, 3 neutrons, 4 neutrons, 5 neutrons, and it goes up and up, 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 up. But they're all carbon. That's saying this is carbon. But guess what? That's carbon too. That's carbon. This is carbon. That's carbon. This is carbon. That's carbon. This is carbon. And that's exactly what happens when this enzyme comes in. It goes, and they go every which way, and these are the only ones they know about. And these are the only ones that are stable, is carbon-12 and 13. All right, when they say stable, they sit around and they don't normally add more particles or give other ones up. But all the rest of them do. So this is a zone of stability. But you can throw a few off this way, throw a few off the other way, it doesn't matter. They're all still considered the same element. And they are not. And in between all the rest of them, there's just every single time you take one away, it becomes another isotope. And you can go all the way from this up until the next one, which is nitrogen. So, and nitrogen, in between the two, they'll have a bazillion different overlaps of particles. Physics is totally wrong. Chemistry is totally wrong. The periodic chart is totally wrong. Speed of light is totally wrong. The universe is totally wrong. Redshift is totally wrong. The planets, everything, 100% is incorrect now. There's nothing that you can stand behind and say to me, Roger, this is right, you're crazy. Well, do it. Say it to me. Somebody, please. Because nothing you are being told is right. Not a single thing. Not a word. All right, this is Sabine Hassenfelder. She's a very good physicist and appears to be quite honest. Now, she's talking about, have we evidence of new physics or not? And that's what she's going to talk about today. I just want to give you a couple of minutes to see what she has to say about looking for this new physics. And she's being very honest, and I give her a lot of credit for being as honest as she is.
That's what we'll talk about today. In a recent article in the CERN Courier, Assistant Professor Carrie DiPatrilio argued for a larger particle collider. She wrote that we know the Standard Model is not the complete picture of the universe. Experimental observations and theoretical concerns strongly suggest the existence of new particles at the multi-TeV scale. TeV stands for tera-electron volt and is a measure of energy. The multi-TeV scale is what the new collider would test. There are no observations or concerns that suggest anything at the TeV scale. Another example, in a recent press release, Jim Fast from Jefferson Lab was quoted with the statement, "We know there are some things wrong with the Standard Model." He said this to explain why we need a new experiment to measure the weak charge of the electron. Makes you wonder how he knows that. Is it those observations or concerns that don't exist? It's been going on like this for a long time. Already in 2018, the then director of Fermilab, Nigel Lockyer, told the BBC that we need a bigger collider because everybody believes there's something there. From a simple calculation of the Higgs mass, there has to be new science. That is, of course, also wrong. For starters, no one can calculate the Higgs mass. It's a free parameter. It's determined by measurement. What DiPatrillo, Fast and Lockyer have in common is that they are all experimental particle physicists. Experimentalists in this field, for the most part, just repeat theoretical arguments. If you push them, they'll admit that they don't really believe what the theorists say, but if it brings them money, it seems they're willing to put their disbelief aside. So let's look at the most commonly used arguments according to which there has to be new physics that supposedly justifies all this investment. It's a really long list, and the heat death of the universe is only 10 to the 100 billion years away. So for...
All right, she's going to get in deep. Now, I'm just into a couple of minutes. If you want to come up and watch it, it's Sabine Hassenfelder. She's very good. And this one is called Evidence for New Physics or Not. And I say absolutely. All right, so Sabine's saying, oh, Einstein's right again. They're all saying this about Einstein. Well, right here shows you Einstein was wrong. You can accelerate light very easily. All you got to do is put a Venturi. And we could separate the white from the black, which nobody even ever knew existed, was the black and the white, except, you know, the particle colliders. They can see them. They find it, but they're just in a pile of debris. We see them actually manifest themselves as they speed up and become photons. Originally, they're neutrinos. I'll show you that in a second. And then they actually divide, which is fission and fusion after the Venturi. And this is what they call them right here. Muon neutrinos and electron neutrinos together, and they smash here, and they divide, and only the electron turns into a shower, a white shower, and the muon just can't get through. And it comes back and joins here. So we see right now, Einstein was wrong. You can accelerate light. Light consists of the dark particle here. Nobody's ever known it. This is just attached to the white one. But when there's enough of them, all the dark ones go to the center. They go inside. So every time we look, it bounces back at us. We see, well, that's just nothing but, you know, there's light coming back at us, so there's no dark matter there. It's in behind, inside. You can never see it because anytime you get even up to the proton size, it's completely coated with the white particles. And here's what it looks like in outer space. The Russians did this. I contacted them long, long ago about this. And it didn't go all that well, but I had my say. They put in charged particles into a vacuum chamber in their space station. And this is what they saw. They freaked out. They said during the experiment, we could contact the Earth guys. Nobody could believe it. One guy locked himself in his room for 3 weeks because they expected to see all the white ones line up like this and this. Everyone pushing each other one away because the white ones hate each other. When you take two white particles that are separated and they're only the white particles, you can't get them to touch. It's called a, oh boy, I can't remember what it was. Kirchhoff, no. Anyway, forget about it. It's two particles can't touch. I'll remember it sooner or later. The fields keep them from actually contacting each other. The fields are what separate things. That's why all the black is pulling all the white in. That's attraction in space. Just like our Earth. Our Earth has to have black hole inside of it, as far as I can determine, because all of the white particles come, they stick to the Earth. They don't just go drifting away. The black sucks it in. And Fermilab has shown this pretty well too. Here's Fermilab's particles. What they do is they take two huge particles like this. Bam! Big ones. Okay, a neutron and a proton. Boom! And all this stuff goes flying everywhere. Well, what did they see? They saw photons. They could see muons and electron neutrinos, and they could see just chunks of this and chunks of that. Because what they did was, instead of hitting two big solid things, they hit two things that were made up of a bazillion particles. And when they did, they went flying. Now, they're still going to get a big chunk over here like that, yes. And they'll get a little one over here like this, yes, one. And a little one over here, and a little one over here. And then they'll get a photon over here. Yes, 100% correct. But it's not because they're two big glass particles shattering everywhere. It's because they're two masses of dipoles that just go flying in chunks here and there, and little ones. All right, I'm going to try to explain this for somebody that's not into this at all. at CERN, they take two huge particles, they smash them together like this, and the protons and neutrons. For me, that's huge, because this, to me, is a proton or a neutron. It's just a ball of little particles, which are the dipoles. But they smash them, and then they just get all kinds of debris. And we would get the same thing, too, if we smash big ones. But we're not smashing big ones. We're smashing these. We're smashing exactly that right there. And what happens is, as it comes in, it forms a photon. Here's the light. All right, let me turn this off. This is red laser. Now, laser is different than normal light or protons or anything, because they consist of all the different colors. Well, when you take laser light, you're got one frequency of light, which means one impact value. And red is very soft. Blue is very hard. It really impacts, and you can do a lot with blue. Red, you can see it very easily, but it's not as powerful. But what you're seeing here is a pulsed red laser. Boop, 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 boop. And then we accelerated it into a Venturi. So light accelerates. Very simple. Very easy to do. And here it exploded. And the white separated from the black, and only the white could get through this very fine slit, very fine pinched slit like this. It's so fine that the black just bounced back out, and the white squirted through. So now that is a complete separation of power. That's fission and fusion, as far as I'm concerned. I can't see how you can see it any other way. That's fission. That's fusion. Before here, it was a complete particle, and here's the complete particle right here. Now, that complete particle has the black and the white attached side to side. That's a photon, and that consists of two, literally, electrons. We never knew about the black part. That's the only thing. Nobody's ever known. That's the dark matter. They say, oh, it makes up 95% of the universe. I believe that, because that's the only thing that has any mass. The white particle is just all field. And that's exactly what they said at Fermilab. The white particle is the point particle. Has no mass, and it has a lot of burn. The black one has all the mass and no burn. It's just, it never changes size. It's called a fixed particle. The other one is a point. It's a point, and it can go to huge. And it just depends on what it's concussing with. See here? These are the neutrinos. They're not fully formed photons. This is a neutrino. This is a photon. That's a photon, and then this is where it collides and it splits and becomes all white. You see the white coming through, and here's the white coming through. Oop. And then we make all the Higgs fields when the white concusses back with the black. That's what a Higgs field is, when the white reattaches to the black. It's not when the white splits away. All right, it's a reattachment of the the white into the black. Now, this is what they see at CERN and Fermilab, which is just nothing more than debris. The red stays around because it's not as tightly held as the blue, and the other one's really down the bottom. They take off, they're gone. They just go and never come back. The red is way out here on the outside already, so it just drifts around and sticks around with that main particle. We never have this situation because they're going with full-blown protons that have all the different energy levels. We only have one frequency, which is red, green, or blue. And here's the blue slowing down, coming in real fast, and then, and you see it drifting. It's spinning to the right, and as it slows, it drifts. The bright spot drifts off to the left, and we can see this made up of two particles. Here, it's so hot that you can only see one. There's two on all of them, which is, they're all photons. They're the same. Here's the green, identical to the red. You see this? Here's the green coming in. Here's the neutrino phases. Here's the photon. This one's just getting ready to spin. You see the white getting all charged up down the bottom? Because it's ahead of the black. It's going to flip to the back, and that white will go out front and start to collect the charge. And that's identical to the red. Identical. And the blue is the same, only the blue is too fast to see, other than just what I showed you here. That's the best we can do on the blue. The blue is a rocket ship. And with the blue, I can turn on LEDs and make them give off energy. But the other two, I can't. And here's what they do. They spin. light spins. You see this? That's what light does. It doesn't flap like a wave. Hold on, let me show you something. This is what light does. It spins like this. All right, and they got a whole batch of them coming. It's not just one. They're all over the place here, these little spinners. I mean, there's a zillion of them. So some of them hit here and go way over this way as they come through. Some of them hit here and go way over this way as they come through. A lot of them come straight through the center. Most of them hit the center. But then some trail off this way, some trail on this way. This is a drill bit. If you look at that, this is exactly what this is, and that's how light spins. Light is a spinner, it's not a flapper. It doesn't flap like that. All right, and so it spins through the Venturi, and that's what gives it that, those, they call them interference patterns. You see they split out here? The white hates each other. That's why they glow like this. You see they're pushing back, they're banging into these. You can't even see these fields. You wouldn't even ever know they're there. This one's quite obvious because it's being forced forward and glowing. It's starting to glow, really glow. And when it explodes here, the back push is what makes these glow. These, you never even see these. They just go by and nobody'd ever know any. You never see any of them, really, if you didn't fire them up. That's because they're fired up, you're seeing them. Now, look close here. I don't know if you'll be able to see this or not. You see those little dots everywhere? You see those little dots? Those are electrons. Those are electron fields from gases. All gases are made out of the same thing everything's made out of, but only smaller quantities. So a gas, instead of being something like this, it might be, their gases are usually really small, so it might be something like that. Or something like this. Once they get up big, they get heavy. Then they get heavy. And then you get into your really solid stuff up here. But down here, helium, oxygen, nitrogen, hydrogen. But way up here, they're not gases. But these are noble gases. These always kind of interested me. All right, just so we can get past this Einstein thing and the expansion of the universe. This is pulse red laser. Light is light. Well, that's how fast it's supposed to go. Well, guess what? This was that same thing, and it's accelerating. If you can't see that, I don't know what I can say. It's gaining energy. All right, mass is energy. I don't discount him saying that, but it has nothing to do with speed of light. Well, it does, if it happens to be in the light realm. But mass is energy. I don't care if it's this thing here or if it's a particle of light. And the harder you throw this at something, the more energy it's going to have, the more concussion it's going to have. The same thing with light. There's no difference. It's just as light. And it doesn't travel at the same speed. That's where he's wrong. There's absolutely no question whatsoever. Zero question. So Einstein's wrong with that. No doubt whatsoever. Now, here's the green and here's the red. The green, at the same time going through the same Venturi, the green is just pushing the red right out of the way. And it's reconcussing way back out here. The green is just, the red is just out of the way, done. The same particles, the same identical particles. One of them spinning much, much faster. And all it is this. The red is like this, coming through. The green is like this. And it just pushes the red right out of the way. It just makes it tumble all the way. All right? And then the blue is like this. It's just like a rock wall coming through there. That's all it is. Speed of the spin, which is the frequency, the distance between waves. By the way, when they say they see waves of light, that's what they're looking at, sideways. You call that a wave. Those are waves. This is a long wave of frequency. This is short frequencies. But it's really spinning. That's what's creating the wave. All right, I just have to make this statement. If we can increase the energy value by doing nothing whatsoever, which this is what this is, That is an increase of energy from here to here. So whatever energy we had to use to put this in, we are exceeding that energy here because of the luminosity. Luminosity is the definition of energy. So this is not very luminous. This is extremely luminous. This is much more energy than that. That means that if we could take that energy, which is extremely luminous and voluminous, by just taking a cheap laser, sending it down, separating the black from the white, right here, the black from the white, and on the other side of the Venturi, because that's all this is a Venturi. It's a little slit. Forces everything to crush. And the fields can crush down and squeak through because they can go small and they can go big. The black ones are just one big ball. It's like a bowling ball. If you can't get through, it can't get through. And it keeps smashing the white ones through because it's a pusher. It'll push the white, but it will not grow or emit energy or any of that stuff. So this is what we want to harvest, and we want to put it down through a photodiode. Means all the photons can come through here, and that's all you want in your battery. When you charge up your battery, it doesn't get real heavy. It just gets real energetic because these things don't weigh anything. They weigh almost nothing. But boy, do they want to get back to that black. And that's what gives you all the energy and electricity, is that coming back together. They call that WIMP. All these guys become all kinds of weak forces. No, it is an extremely strong dipole electron force. These are dipole electrons, and they want to be together so desperately that you can't hardly get them apart until you put them through this Venturi, which forces the white to squirt through. And I can show that. I mean, there is no question that this is true. This is it right here. The white is coming through, the black is not. And this is how it started. And this is where it hit right here. This is it right here. This is it right here. The white can get pushed through because this can get big and small. See it? And this one here is getting big right now because it's getting knocked into by all of the particles it has to go through. This light is coming this way. And very shortly, this one will charge up and flip to the back, and that will go to the front. That's what you see when you see the particles. They're spinning, really. It's not like they're flipping this way. They're actually spinning this way. Anyway, these are the particles. Now, they see them right here. Whoops. This is from Fermilab. They see the same particles, only they see them from just gigantic big collisions of debris. We are down in the realm that they should be in. They keep making bigger machines, just, I don't know why. You don't need a big machine to do this. This was done on a desktop for a very, very small amount of money. And this was what came out. And the red is exactly the same as the green or the blue. And there's the Higgs fields, all the stuff they found. Here's just standard light. Here's light accelerating. Here's light dividing. There's fission and fusion. And here, my friends, is something that it appears to be a reverse spinning particle that got caught up with a forward spinning particle, which ripped off the edge. But this is what they see at CERN and Fermi. Like I said, well, too much. We're using this. And now they're building bigger and bigger and bigger. And in another 30, 40 years, we're going to figure this out. Well, I don't know. I guess they do what they do, and we pay for it.